we're going to learn about GCD and LCM. Okay, so the greatest common divisor, hence it is very common. Because we want the greatest of them, we are taking alpha I to be the greatest possible, whatever it can take. LCM and GCD, that you take the product and that will be equal to the product of the two numbers. So in today's lecture, we are going to learn about GCD and LCM. This is also a very commonly known topic, very famous topic in number theory. So we are trying to get rid of all this normal stuffs to get into the most interesting stuff which is coming ahead. Yeah, congruency of integers, that's like one of my favorite stuff. That will be coming towards you tomorrow. Also, please let me know in the comments, not in the live chat, in the comments, whether how are you finding this? How are you finding this idea? Do you want us to tweak a little bit so that the timetable is too hectic every day? So let us know how is it going, if it's getting boring or what. Okay, so let's see. Yeah, let's go ahead. So welcome to this video again, and we're going to start. Okay, so the greatest common divisor, of course, as we know, the divisor is, so we generally talk of this in two terms, of A and B of two integers, right? So if D divides A, D divides B, that would imply that D is a common divisor. Yeah, D divides A, divides B, then it is a common divisor, and naturally D would be smaller than A and B. Right, it will be smaller than A and B. So the greatest of such common divisor will be a unique one. So the greatest such one, greatest such divisor would be unique. To A and B. Okay. Hence it is very common. Now how do we calculate it? Now in the previous session about divisors, we talked about how to find a divisor, so or how to look at a divisor in terms of prime factorization. So let's talk about prime factorization again. So let A, okay, let me change the color. Let A be P1 power K1 till Pn power Kn, and B be P1 power say L1 times Pn power Ln. So why would there be same number of primes in the prime factorization? There need not be, but if there is, for example, these Li's could be 0 also, right? This Ki and Li could be 0 also. So if A has 2 into 3 into 5 and B is 3 into 7 into 11, then we can write this as 7 into 11 power 0, and we can write this as 2 into 3 power 0, or 2 into 5 power 0, right? So all the prime numbers could be written in the prime factorization, just we have to take the power 0. So what's going on? Now T divides A and B both, it implies that if D is equal to P1 power I do not know alpha 1 till Pn power alpha n, that would imply that alpha 1 is less than or equal to both K1 and L1, and so on till alpha n, that will be less than or equal to Kn comma Ln. Now, since it is the greatest, so it has to be less than or equal to both. So, can I say that each alpha I has to be less than or equal to minimum of K1 comma L1? Think about it, Ki comma Li. So a number alpha is less than or equal to both 3 and 5, let us say. Doesn't that imply alpha is less than or equal to minimum of 3 and 5, right? Hai? Now, we want greatest such D. What does that imply? All the alpha i's must be greatest possible. Right. So, we can, so and each alpha I is less than or equal to minimum of Ki comma Li. That would imply that the GCD A comma B will have alpha I equal to minimum of Ki comma Li. Yeah, makes sense. Because we want the greatest of them, we are taking alpha I to be the greatest possible whatever it can take, right. Now, this representation is very important, because now GCD we got it in terms of the prime factorization as well. GCD also we got in terms of prime factorization. There is another way to look at GCD, right. It is by Euclid's algorithm. So, what is Euclid's algorithm? Euclid's algorithm says that A is equal to BQ plus C plus R, right. Now, what Euclid did is he took now B as the divisor, is the dividend or divisor, and R as the other thing, and then you will get some Q1 plus R1, and then he will take R as this, Q2 plus R2. He keeps on doing this till there comes a point when Rn equals Rn plus 1 into some Qn plus n plus 2, and there is no remainder, right. So, what does that mean? And he says that this particular term is the GCD. Now, why is this true? We have seen this in our school days, right. Everyone has seen this, but we never really understood, I believe. At least I did not for a long time. I had to think about it by myself. So, at the end the common thing is, you see that this term is a factor of this, yeah. So, GCD would divide both A and B, right? And that would mean that GCD would divide this also. It would follow from the fact that GCD of A comma B is equal to GCD of A comma B minus A, or GCD of A comma B minus 2n, and so on till GCD of A comma B minus NA for any n. Now, why is that true? Let's try to investigate into that. So, if D divides, so I just want to prove that GCD of A comma B is equal to GCD of A comma B minus A, right? This is what I need to prove first. Okay. So, let D be the GCD of A comma B, which implies D divides both A and B, which also implies D divides both A and B minus A. There is no problem till now. Now, to show that this is the GCD, we have to let D1 divide A and B minus A such that D1 is greater than D. We are assuming that there is some divisor which is greater than D. If we find this to be a contradiction, which that proves that D is the greatest common divisor. Okay. Now, we know that D is the greatest common divisor of A and B. So, if D1 divides this, that implies that D1 divides A comma B, which implies D1 has to be less than or equal to D. Do you understand? From here to here, why did we get? Because we are simply adding two terms. If D, so the thing about divisors, right? If D divides A, D divides B minus A, that implies D divides A plus B minus A, right? So, plus or minus, so that is what we get. So, this is not possible, not possible, right. So, that would tell us that D is GCD of A and B minus A, and hence directly from here it follows that GCD of A comma B is equal to GCD of A comma B minus NA. Now, why is that important? It is important because if we can write B is equal to AQ plus R, then that would imply that GCD of B comma A is same as GCD of B comma R. And now, I will write A here, A is equal to R Q1 plus R1, and that would imply this is equal to GCD of R comma R1, and so on. It goes to the point till some Rn will be equal to Rn minus 1 Qn plus 0. So, when that happens, it is simply GCD of Rn comma 0, right. At the end, if okay, what is GCD of something comma 0? GCD of A comma 0. So, the D should divide A and D should divide 0. All numbers divide 0, right, and it has to be common. So, what is the greatest? This has to be A, right, that is simply Rn. That is why Euclid's algorithm works, right. I hope I made that clear. Okay. Now, let us talk about LCM. What is LCM? Least common multiple. Again, if A divides M and B divides M, then M is common multiple of A and B, and A is less than or equal to M, B is less than or equal to M, right. That should imply that if we take least of such M, then that will be unique. Yeah. So, again that will be unique, that is a different thing. So, again if I have in terms of prime factorization, I think I should give it to you as a homework, right. Take it as a homework. To prove that if A is equal to P1 power K1 Pn power Kn and B is equal to P1 power L1 Pn power Ln, then LCM of A comma B will be P1 power beta 1 till Pn power beta n, where beta I will be maximum of Ki comma Li. Prove this on yourself. So, we did the very similar thing for GCD. I want you to do it for LCM, and it is not difficult at all. So, take it as a homework, do it as an exercise, and you can even send it to me, right. So, you can send it to me at right, this is H Anirudha Chakri. Yeah. All right, is that readable? Chalo. Now, a few properties of LCM and GCD is, what's the time? 18 minutes, not bad. LCM and GCD, that you take the product and that will be equal to the product of the two numbers. That is very interesting, because since we know that LCM of A comma B, take the powers का maximum, right, इसका product है, and GCD of A comma B is product of PI's minimum. When you multiply them, what happens? When you multiply LCM into GCD, the Pi ka power becomes maximum of Li comma Ki plus minimum of Ki comma Li. Now, max of K comma L plus minimum of K comma L, wouldn't that always be equal to K plus L? Since you are just adding, one of them will be maximum and one of them will be minimum. Whatever the order be, when you are adding, it will simply be K plus L, right? So, this will simply be Pi power K plus L, and that would give you A into B. Yeah, isn't that obvious? Right. Now, this we discussed, right? This we discussed. I hope that is clear, and for exact same reason, if you have GCD of n comma 1, it will always be 1, right? Because this is simply GCD of n comma n plus 1 minus n, right? And this is going to be this is always 1. Why? Because if d divides 1, then it has to be 1, right? And whereas GCD of n comma 0 would always be n. Interesting, right? So, I hope this is clear. Oh, I thought, oh, and by the way, GCD can be written in terms of, so if D is equal to the GCD of A comma B, then there will exist x comma y belongs to integers such that D is equal to Ax plus By. Okay. So, that will always exist. How do we know that? Because it comes from the Euclidean algorithm itself. So, if you look at the Euclidean algorithm, what do we do? Again, let us get back to Euclidean algorithm. So, we write A is equal to BQ plus R, Q is B is equal to B is equal to RQ1 plus R1, R is equal to R1Q2 plus R2, R1 is equal to R2Q3 plus R3, and so on. But let us assume that it terminates after these steps. Let R2 is equal to R3Q4 be the final final step. That would imply that this is the GCD, right? Now, we got R2 in terms of R3. So, we can write this as R3 Q4 Q3 plus R3. So, it is simply R3 into something, some A3, let us say, right. So, we wrote R1 in terms of R3. Now, we put the R1 here, and we know we can write R2 in terms of R3 as well. So, this can be written in terms of R3 plus something, right. okay, maybe this won't work because at the end we will probably end up with the initial equation. Okay, let's do something different. Oh, do we have undo? Okay. Okay, this should be an interesting observation. Okay, maybe instead of this we will do with some example that will be easier to see. Let's take example. Let's find GCD of I don't know, 120 and 50, right? 120 and 50. So I can write 120 as 50 into 2 plus 20. I can write 50 as 20 into 2 plus 10. I can write 20 as 10 into 2. Right? So this happens to be the GCD. Now I'll write the GCD in terms of 10 and 20. So 10 will be 50 minus 20 into 2, and I can write this 20 as 120 minus 50 into 2, right? Now substitute this 20 over here. So I can write my 10 as 50 minus 120 minus 50 into 2 into 2. So I have my 10 as 50 minus 120 into 2 minus 50 into 4. So this is 50 plus. So 50 into 5 minus 120 into 2. So that's how we do it. It is very interesting, right? I hope you understand. So each of these terms you write in terms of the others, and at the end you want everything in terms of 120 and 50. This you can do for any two numbers. Let's say I have the numbers okay, let's say I have the numbers 126 and 34. So 126 can be written as 34 into 3 times, right? If you take 3 times, it's 102, which will be 24. So 34 can be written as 24 into 1 plus 10. 24 can be written as 10 into 2 plus 4. 10 can be written as 4 into 2 plus 2. So at the end this is going to be left. 4 is equal to 2 into 2. So this is the GCD. Yeah. So now write each of these. Here you can write 2 is equal to 10 minus 4 into 2. Here you can write that 4 as 24 minus 10 into 2. You can write the 10 as 34 minus 24 into 1, and you can write at the end 24 as 126 minus 34 into 3. Now, so you substitute the value of this 2 here, and then you substitute the value of this that's what we did, right? That here in terms of 50 and 20, and yeah. So substitute value of this 2 here. No. I'm talking in it in the reverse direction. So I'll change the color. So you have 24 in terms of 126 and 34. So you put that value of 24 here. So you'll get in terms of 34 and 126. Now you take that value of 10 and put it over here. You have the value of 10 in terms of 34 and 126, yeah, and then you put this value of 4 over here. So at the end you have the whole expression to be in terms of 34 and 26, because you already have 24 in terms of 126 and 34. So you will get 2 in terms of 126 and 34y. So that is one way of looking at GCD. Yeah, I hope you are able to follow. Okay. Yeah, a few more properties. This is something interesting. So you must note that if D is the GCD, then A can be written as D into X, of course, because it is a divisor, and B can also be written as D into Y, where GCD of X comma Y is equal to 1. We call these kind of numbers co-primes. Right? You call these kind of numbers co-primes. And this happens, and then LCM becomes A comma B is equal to D into XY. You can follow these results from the result of, you know, prime factorization. You can follow this from that directly. Euclid's lemma. Okay. So this says that if A divides BC and there is no common divisor between A and B other than 1, 1 is always a common divisor, and if other than that, if A and B don't have any other common divisor, that would imply that A should divide C. Now this should be something very intuitive, right? Okay, even if it is not intuitive, let's try to prove it rigorously. So since GCD of A comma B is 1, there will be x and y such that Ax plus By is equal to 1. Okay. So C will be equal to ACX plus BCY. Now I want you to see that ACX can be written as C minus BCY. This is divisible by A, right? Yeah, and this is also divisible by A, given, or rather here only you must see that this is divisible by A, this is divisible by A. That should imply that A must divide C, like it is a very obvious thing even if you do it rigorously. Now, okay, this is questions for today, I don't know why I didn't write the heading questions for today. So, part A, how would you do that? So, first of all, for A, we use extensively for this part of question, we use extensively the GCD of A comma B is equal to GCD of B comma A comma B minus NA for any n, for all n, that should be true. Okay, so 2a plus 1 GCD of 2a plus 1 comma 9a plus 4, that should be equal to GCD of 2a plus 1 9a plus 4 minus 4 into 2a plus 1, right, and that is equal to GCD of 2a plus 1 times minus so 9a plus 4 minus 8a plus 4. So, that is simply GCD of 2a plus 1 comma a, right. Yeah, that is GCD of 2a plus 1 minus 2a comma a, which is GCD of a comma 1, which is of course 1, right. Clear? Is that clear? In fact, I would like to give B as a homework. Take this as a homework and we will do this. This is simple, irrespective of whether A A is odd or not. GCD of 3a comma 3a plus 2 is simply GCD of 3a comma 2. So, that would imply that this is same as GCD of 3a comma, now we will take that A is odd, A is equal to some 2a plus, I do not know, 2a plus 1. So, 3a 2b plus 1, let us say. So, 3a will be 6b plus 3. So, we have 6b plus 3 comma 2. Now, I will subtract 2 or maybe I can subtract 2 3b, right. So, this becomes GCD of 6b gets cancelled. So, 3 comma 2, which is 1. So, this is always 1, this I want you to do as homework. Yeah, sure. Oh, yeah. So that's the end of this session. I didn't realize that slides were over. Okay, today was not that long, and I hope you really enjoyed this session, and we'll meet soon in the next session. So, this week's schedule will be followed as we planned, and I want you to give your suggestions to see how you are liking this. So, yeah, let's go. Yeah, bye, take care.